Hello everyone, welcome back to my channel. In this video I will talk about how to build a very rudimentary but quite useful artificial load. There are plenty of other videos out there on YouTube where various electronists are building DC loads or electronic loads or electronic DC loads. All of these three names specify basically the same thing. And there are plenty of tutorials that are showing quite elaborate and advanced schematics of building these devices with advanced functions. However, sometimes we need something fast, cheap and dirty to just get a jump done. Sometimes we just need to be able to draw a certain current from a certain power supply to be able to test it and just have minimum control over this process. So we don't necessarily need an electronic DC load with digital circuits that have high precision and come with a display and software and menus and all sorts of things. So for this particular purpose I present to you this very simple DC load. Well, actually it's not just a DC load, let's call it artificial load in general. I cannot call it DC because in some cases it allows AC to be applied to it. And I cannot call it electronic load either because it's not an electronic load. It doesn't have a digital circuit with displays and digital controls and stuff like that. So I will just call it artificial load. For those of you who don't know, an artificial load can be used in quite a few cases. We will use it when we want to test a power supply. When we want to test whether or not it gives the amount of current that it's supposed to give. We use an artificial load when we want to test a transformer and also to identify what its maximum power is. An artificial load can also be used to test the batteries and rechargeable batteries and see how much they last, how fast they discharge, etc. And in some cases we also want to be able to test high power amplifiers, audio amplifiers, and we cannot just connect them to speakers just like that because it can get very noisy and maybe we want to perform a longer test on a longer period of time. So the simplest way we can accomplish this is to attach a power resistor instead of a speaker to that power amplifier. And for this we can also use this this artificial load that I'm presenting to you. So without further ado, let's delve into the schematics and let me just quickly show you what this is all about. Everything's simple, it's easy, it's a very easy project that can be done by beginners without a big problem. It does not require a PCB. All the components can just be connected through wires, soldered between them through wires, and that's pretty much it. So let's delve into the circuit. Okay, so this is a schematic. As you can see, it's pretty simple. It's divided into three areas. This area with a bit of a light pinkish background. This area with a light green background. And this area over here with a mains power connection, on-off switch, a power supply, 12 volt 1 amp, a panel meter and some fans. Ignore the fact that it's not written in English, it's written in Romanian. I will explain everything there is to know, so there will be no ambiguities, there will be nothing that you will not understand. And so the main area, the main part of the circuit that is going to draw current from whatever we connect to the input is this one with a pink background. It's comprised of 4 resistors, 4 power resistors. Now, due to availability and economic reasons, I chose to actually have groups of 2 resistors. So instead of each resistor here, I actually have pairs of resistors placed in parallel. I will explain a little bit in a little bit of moment why. So the idea is that by having 1, 2, 4 and 8 ohm resistors, we can create combinations of them, and we can have higher or lower equivalent resistance, which applied to DC, which applied to an input voltage, is gonna allow us to draw quite a wide range of currents. Now, in order to place these resistors in parallel or in series, in order to connect or disconnect them from the circuit, we have these 4 upper switches and these 6 lower switches. The upper switches are very simple, just on-off switch that connects or disconnects each resistor. The lower side switches, these 6 ones, labeled A, B, C, D, E and F, they are single pole double throw switches. Basically, the way they are connected allows us to connect any resistor in series or in parallel with any other resistor. That's why I have 6 of them right here. That's why they are connected this way. And I will show you a little bit later what are the values that we can achieve with connecting them in series or in parallel. Now, as I've said, these resistors are power resistors. They need to be able to withstand 100 watt each, or at least that's what I chose. Having a 100 watt power is good enough for us to be able to apply a wide range of voltages and currents at the input. And it should be a wide enough range for us amateurs to be able to work with many devices. Now, because I couldn't find 100 watt resistors of these values, 1, 2, 4 and 8, I couldn't find all of these 4 values, and on top of that, the 50 watt resistors were actually cheaper than half of a single 100 watt resistors. What I did is to choose to buy 50 watt resistors and place them in parallel, so that together they form a 100 watt resistor. And in order to do that, I had to choose double the resistance, so that when placed in parallel they halve their resistance value to what we actually need. Now, for the 1 ohm resistor, I couldn't find a 2 ohm resistor of 50 watts, so I found a 2.2 ohm resistor, and placing them in parallel gives us 1.1 ohms. Not a big problem. For the 2 and the 4 ohms resistor, I actually found 4 and 8 ohm resistors, so placing them in parallel gave me exactly 2 and 4. And for the 8 ohm resistor, I also couldn't find a 16 ohm one. I found a 15 ohm resistor of 50 watts. So I bought 2 of them, and well, 15 divided by 2 equals 7.5. Not a big problem, because it's not a huge difference between 7.5 and 8. And if we choose to couple it with a 1.1 ohm, it gets even closer to as if it were 8 ohm. Okay, moving on, we also have this block in here made by one power transistor, BD 911 in my case, but it can be any other power transistor for that matter, 2N3055 or any other power transistor. Another power resistor, this time it's a 5 ohm 50 watt one. It can be also another value, but I don't recommend going up too much. And there are also two potentiometers. In my case, I just used a couple of potentiometers that I already had salvaged from various devices, various old devices. One is 50 kilo and the other one is 10 kilo. Basically, with these two potentiometers, we can adjust the amount of current that this transistor will apply to this resistor, and therefore the amount of current that this particular piece of circuit will draw from the input. So the thing is, with these four power resistors, or should I say groups of resistors, even though we can apply them in series or in parallel and make all sorts of combinations, the number of combinations that we can create are limited, and therefore the currents that we can draw with them from the input device are also limited to certain values. But there are certain cases when we just want to adjust, to have a fine adjustment of the current that we are drawing from, let's say, a power supply. That's why I have created this circuit with a power transistor in parallel with this other circuit with only resistors, so that we can adjust the current that we're drawing much better. And this is also the reason why I have two potentiometers here, so that I can have a sort of a coarse adjustment and a fine adjustment as well. Anyhow, these two circuits are separated by double pole single throw switch that basically connects and disconnects them. And the main reason is that, like I said, this device can accept both direct current and alternative current. But the problem is, this particular piece of circuit with a power transistor can only accept direct current. It cannot accept alternative current. However, we can apply alternative current to these power resistors. So, in order to separate these circuits, so that when we want to work with AC, this circuit should be disconnected, I have attached this switch over here. And on the front panel I have created two sets of inputs, one for DC and one for AC. So basically, if you test something in DC, like power supply, you can easily apply it to the DC input, switch this switch on, and you can work with both circuits. If on the other hand you want to work with AC, maybe you want to test a transformer or a power amplifier, you will connect to this input, AC input. You will decouple this switch. You will switch it to the 0 position, to the off position, so that the AC current only gets in here in this circuit with power resistors. On top of that, if you're working with DC, you most likely would like to see in real time what voltage you have on this input and what's the current that's being drawn by this device. That's why I've put this panel meter here. This panel meter is a device that can be bought as it is. It needs a power supply, That's why I have this 12 volt 1 amp power supply. It doesn't actually consume 1 amp. However, all of these power components need to be mounted on a heatsink, and in order to help the heatsink cool down better, we would like to have some fans blow air on them. So that's why I chose this power supply of 12 volts, because we can easily use computer fans, and 1 amp because we can easily put 2 fans that will draw, I don't know, 500 or 600 milliamps together. So we need at least 1 amp from our power supply to power them and this panel meter as well. The panel meter is also connected to the input DC plus connector for the voltmeter plus connector inside the panel meter. Also, the DC input minus connection on the front panel of the device has to go to the ammeter minus input on the panel meter, and the ammeter plus connector on the panel meter has to go to the rest of the circuit. This way we are connecting this panel meter so that it can measure both voltage and current at the same time. And that's pretty much it in terms of schematics. Like I've said, this schematics does not does not require a PCB, simply because there are no components that can be attached to PCBs. All of these 4 power resistors plus this extra power resistor and this power transistor, sorry. All of these components must be placed on a heatsink, and therefore connections between them will be done through wires soldered. All of these switches, all of the 4 switches above and the 6 switches below, plus all of these switches, the on-off switch, the DC coupling switch, plus the 2 potentiometers here, will be mounted on the front panel, obviously, because we need to control them. So again, these are components that will have to be connected to the rest of the circuit with wires. The panel meter will be also placed on the front panel, and we can just buy it as a device. We don't need to assemble it. We don't need to create it ourselves. The power supply as well, you can just take any power supply that gives 12 volts and at least 1 amp from any old device that you just don't need. You just take it and you put it inside of this device, of this artificial load. Anyway, let's move a little bit to discuss a bit about the theory behind this artificial load, and why I chose these values for these resistors, and just so that we can better understand why we chose this design. Okay, so you will be able to download a zip file with an archive, basically, with all sorts of files necessary to build this project. And amongst these files you will also find this Excel table. I will quickly go through it and explain a bit about the theory behind this device so that you can better understand it. Ignore the fact that whenever I needed to write something, I wrote it in Romanian. I will explain everything, and besides, there aren't many things written in words. Most of them are just calculations. So the first sheet that you will find inside this Excel table will have a table with inputs voltages and the various currents that we want to draw from the input device. Like I said, this device is basically meant for amateurs like me. As amateurs, we will never work with voltages more than 24 volts, maybe occasionally more 30 volts, but never more than 30. So that's why I created this table up to 24 volts. Also, most of the times we will be working with 5 or less amps. This table is calculated up to 10 amps, and this device can draw up to 10 amps for a lot of these voltages. So the first sheet contains a table in which for each combination of voltage and current that we want to draw, I have calculated the resistance that we need to insert into that circuit, into that let's say power supply, if that's what we want to test, so that for that particular voltage we can draw that particular current. And as you can see, I have marked in various colors the 1, 2, 4 and 8 ohms value, as well as the 15, or a value as close to 15 as possible, which is basically the sum of 1, 2, 4 and 8. And this was so that I can see so that I can have a quick glance of the total amount of combinations that I can make, so that I can quickly see how many combinations will this artificial load be able to handle. And as you can see, the surface of this table is covered pretty well. There are only a handful of combinations of voltage and current that give a very, very low resistance. And there are a few others who give very high resistance. But we will see in a bit that these are not that much of a problem. So this was basically the main reason why I chose 1, 2, 4 and 8, or in my case 7.5 ohm resistors, because with them we can make pretty much all combinations, almost all combinations of voltages from 0 to 24 and currents from 0 to 10 amps. In the second sheet, power, we basically have the same table, but instead of calculating what resistance we need to place into the circuit so that we can draw that current, I have calculated how much power does that resistor need to be able to withstand for each combination of voltage and current. The main reason was so that I can see where exactly will I hit the 100 watt limit. And apparently we need to get past 5 amps in order to hit this limit. We will reach it at 5 amps as well, 5 amps and 20 volts. But up until there we will not reach this limit. So basically any combination up until that point will be able to be done easily with this device without being afraid of burning it. The third sheet of this table basically contains a coverage graphic, let's say. I haven't calculated real values here, but rather based on the first two sheets, I have calculated what combinations of voltages and currents will we be able to easily create with this artificial load. and what are combinations that are a little bit trickier or problematic. Green cells signify combinations that can be easily done at least with 4 power resistors groups, like this one. Okay. And as you can see, green cells are the majority of this surface. Blue cells represent cases when we want to draw a very small current or relatively small current for those particular voltages, and we won't be able to use the 4 power resistors. Instead, we will have to use this circuit with a power transformer, with a power transistor, sorry, and the 2 potentiometers. The black cells here represent relatively high voltages and very low voltages. These will be even more difficult to obtain. Not completely impossible, but more difficult. We will have to turn those potentiometers really slow and be very careful about how we handle the device, because it's not going to be easy to draw such a small current from such a large, such a high voltage. But again, it's not impossible. On the top right corner of this table, we find a few cells that do not have any kind of color applied. These are cells that show us combinations that cannot be done with this device, no matter how hard we try. These combinations basically require such a low resistance that no matter how we take all of those 4 resistors and we combine them, we just cannot obtain them. So basically, these combinations cannot be obtained with this device. These are way too small voltages, 2, 3, 4 volts, for example, and way too high currents, 4, 5, 10 amps, etc. On the other hand, on the lower part of the lower right bottom corner of this table, we have some combinations that are possible, but they basically require high currents to be drawn at relatively high voltages. For these combinations, we have to be really careful not to burn our resistors, and we have to perform some calculations in order to see for each particular resistor what current is passing through it, and calculate the power that it dissipates, and make sure that it is safe for us to apply that voltage and draw that current. The third sheet is pretty much similar with this coverage, except I have a table with minimum and maximum current that can be drawn with this device from each voltage. On top of it, I have added also the current that can be drawn with that small circuit with a power transistor. And I have made a graph so that I can easily see if at a certain voltage I can draw a certain current and about where are my limits. The fifth sheet of this table contains a small utility in order to calculate for a certain voltage. U is voltage. For a certain voltage and a certain resistor values that we place in parallel, only in parallel, what are the currents, what is the total current that passes through them, and what power does each resistor dissipates, right? So this is useful to know whether or not we can use this artificial load for a certain voltage and a certain current. So you will come here and replace these values. This is for 2 resistors placed in parallel, and this is for 3 resistors placed in parallel. You will simply replace these values, and the Excel sheet will calculate automatically all of these values in red. The equivalent resistance of this circuit, the power for the first resistor, for the second, for the third here, and the total current that will pass through that circuit. The 6th and final sheet of this table contains a list of possible combinations and possible equivalent resistances, so that you don't have to always take a look at the schematics and try to figure out how you need to switch those switches up, down, etc. in order to create a certain value for the equivalent resistance. You have here a table that goes from the smallest resistance, which is around 0.56 ohms, up to the highest resistance, around 14.6 ohms. And you have here a table of all the switch combinations, so that you know if you need to switch it up or down. The first ones, 1, 2, 3, 4, are basically these ones on the upper side of the resistors. Switch 1, 2, 3, 4. And these ones, A, B, C, D, E, and F, are the lower side ones. Okay. If you have a black cell in the upper side, it means that that switch has to be turned on or up, respectively. If you have a black cell on the lower side, then that switch has to be turned off or pushed down. Okay. If you don't have a black cell anywhere, it means that that switch just doesn't matter what position it has. Also, you have in the P column here explanations for each combination, so that you know exactly what resistors get placed and how, so that you know if you need to come here and perform some calculations in order to see dissipated power for each of the resistor. You will know exactly which resistors get connected in order to obtain that particular resistance. 2 vertical lines means that the resistors are placed in parallel. Okay, so to take an example, this 0.6 ohm total resistance can be made by placing the 1.1 with the 2 and the 4 ohm resistor in parallel, all 3 of them. And in order to achieve that, you have to switch the first, second, and third switch on. The fourth one has to be switched off, and then you have to push down the A switch, D switch, and F switch. B, C, and E do not matter how they are placed, what is their position. Okay. If you see more complex combinations like these with plus and values placed in parentheses, this means that there are some resistors placed in series. Plus means placed in series, and together they are placed in parallel with another one. So for example, the 3.04 ohm equivalent resistance is being done by placing the 1.1 ohm and the 4 ohm resistors in series, and both of them placed in parallel with the 7.5 ohm one. And again, in order to do that, you need to switch on the switch number 1, off number 2 and 3, switch on number 4, and then switch up the A switch, switch down the B one, switch up the C one, and switch down the F one. And that's how you get this value. Last but not least, I want to quickly show you how I've built this device. Although, of course, you are free to do it in any other way. I have simply chosen to make myself a wooden case, a wooden chassis, if you want. Basically because it's, for me, it was a lot simpler and faster. I have all of these power resistors placed here on this custom heatsink. I will make a separate tutorial on how to build a custom heatsink. I have attached on the front panel all of those switches and potentiometers and panel meter. Like I've said, I have just taken a 12 volt 1 amp power supply from a different device that I didn't use anymore, and I just placed it here inside. You can do the same. I have mounted a couple of computer fans on this heatsink so that it helps with cooling. I strongly recommend that you use thick cables to connect everything because strong currents must pass through them. In the archive with project files, I will also add a short schematic of the back of the 6 switches so that you can easily know how to solder them together, how to connect them together. They can be connected together through just conductors, through just wires, and it's really simple. Also, inside this archive project, you will find a PDF file with that list of resistance values and that table with switch positions. A little bit formatted better for printing on a sheet of paper, so that you can just print it and glue it on one side of the device case, so that it comes in handy and you can just easily take a look at it and know exactly how to switch the 10 switches, the 1 to 4 ones and the A to F ones. So that's about it. Thank you very much for watching, and I'll see you to the next tutorial. Thank you, bye.